Now that we've seen how these different sets have same cardinality as other sets, we like start to define and give names to these sizes. Because we saw, for instance, that the interval 0 to 1 had the same cardinality as all the real numbers, and we had all integers had the same cardinality as the natural numbers and things. So let's take a look at some of these names. So the set is called finite if it is the empty set or has the same cardinality as 1, 2, 3, all the way up to n for some n of the natural numbers. So we're basically talking about finite sets. Empty set is going to be a finite set, and anything else where you have a perfect matching between, say, 1, 2, 3, 4, that's going to have the same cardinality as that, which is going to be finite. Okay. Now, that's finite infinite then is that it's not finite. So it's a set that is not finite. A set is countably infinite if it has the same cardinality as n. So you can talk about now this idea of countably infinite, just having the same cardinality as n. So for instance, the integers have the same cardinality as n. The even integers or the even natural numbers, those have the same cardinality as n. So those are all countably infinite. The set is called countable if it is finite or countably infinite. So we start to group these together. If countably infinite and finite form countable. And then we have the set is uncountable if it is not countable. So makes sense. So basically, infinite is not finite, uncountable is not countable. So, but notice here real quick, countably infinite is not the same thing as infinite. Is countably infinite actually infinite? I don't know. I mean, we'd have to try to prove something like that. So let's take a look at some examples. So the set containing 1, this is a set, it is finite. So if it's finite, that also means that it is countable because it is finite or countably infinite. So it is finite and it is countable. It's obviously not infinite because it is finite. Countably infinite, well, that's a little harder to prove, right? What number would, if it's the same cardinality as that natural numbers, well, that doesn't make sense, right? And if it is not countable, but it is countable, so it's not uncountable. So the natural numbers now, that is not, I don't know, maybe it doesn't seem like it should be finite. I don't know, maybe it's infinite. I don't know, but just looking at the definitions, I know for certain that it is countably infinite because the natural numbers have the same cardinality as itself. So the natural numbers is countably infinite. And obviously then it is also countable. So it is countably infinite as well as being countable. So now we have these questions. Are there infinite sets? Do infinite sets even exist? And are there uncountable sets? So we have these two because it basically says that if it's not finite or if it's not countable. So you could prove easily that things are finite and things are countable. But to show that something is not that, it gets a little tricky. Right, so we could take a look at a proof of how we could try to show that the natural numbers is infinite. Right, so that seems to be a very good starting point, that if I can show that the natural numbers are not finite, then I could prove that it is infinite. So we will prove that the natural numbers is infinite. So prove that this is an infinite set. So if you're thinking about how would you prove that, the first technique that you should be thinking of is contradiction, right? If we're trying to show that it is not finite, well, then we'll assume, what if it is finite? So our proof is going to be suppose to the contrary that n is finite. So let's suppose that it's finite. What that means then, if it is finite, then it's either the empty set, which we know clearly that's not the case, or it has the same cardinality as some set from 1 up to n. So we will say, suppose n is finite, then there exists a bijective function f that's going to map the natural numbers into the set 1, 2, up to n for some n in the natural numbers. So remember, so to show that they have the same cardinality, or to state that they do, that means that there exists a bijective function that maps between those. Now, when we think about how do we get a contradiction about this bijective function, well, there's two components of it being injective or surjective. So one of those two we will try to argue now is not true. Now, if we think about which one is going to be the one that's not true in this case, well, we could probably make this surjective, right? I could probably have all of these elements in the codomain have something to get mapped to. But injective, on the other hand, that gets a little bit trickier. So you could try to prove this with injective. On the other hand, if you think about it, well, what if I could do surjective? Which one's going to be easier? So when I think about those two, well, I actually think that surjective is easier to prove. So I'm going to flip these around. So I'm going to say the set 1, 2 up to n is going to get mapped to n. So now I'm going to try to show that there's something in here that doesn't get mapped to. So we will now state, let f of k be the largest value in n for k equaling 1, 2, up to n. So I'm going to work with, because I know the natural numbers start at 1, they go on forever. I'm going to pick f of k. That's going to be the largest value that gets mapped to from all of these. So we take all of the elements. We know they all have something that they get mapped to in the natural numbers. Now, because there's only n of them, I can pick the biggest one. There exists this largest one. So I'm going to say f of k is going to be that value, or I'm going to say, maybe call this guy z. So let z be f of k. That's the largest value in the natural numbers for any k here. Notice z plus 1 is in the natural number. So remember how we defined the natural numbers was saying that you had this recursive idea, or this successive function that you can always add 1 to and get the next natural number. So we know that z plus 1 is in the natural numbers because z is going to be in the natural numbers. Z plus 1 is in the natural numbers, but z was the largest value mapped to in the codomain. Mapped to in the codomain. Now, obviously, this also gives us a new natural number, so we indeed have that there's something in the codomain that was not mapped to. So this implies that f is not surjective. So if it's not surjective, then immediately we know that it is not bijective. So f is not surjective, which implies that f is not bijective. And because we just worked with any arbitrary function, I didn't try to assign a specific function. Any function that I try to define with this does not work. So what this means here is that, therefore, n is infinite. Because it is not finite, that means that it is infinite. So we have indeed shown the existence of an infinite set using this contradiction proof.